This unit is based on solid, liquid, and gas. This particular video will focus on gas. Now, the gas had various subcategories as well. The properties of gas, gas law, and ideal gas law. I'd like to talk to you about the ideal gas law. Now, let me give you two different scenarios of my breakfast. An ideal breakfast would look something like this. I would have a great oatmeal, maybe a latte from somewhere fancy, and then I would get a boiled egg. This would be a very typical ideal breakfast. But the reality is it doesn't look anything like this. It looks more like this. My children's leftovers, maybe jam that was left over from jam and toast from, from the morning. This is what I just stuff it in a Tupperware and then I'm eating in the car. Sometimes I even get strawberries, the end of the strawberry, where my kids got the better part of the strawberry. And then I would grab a cup of coffee at McDonald's or something like that. That's a reality. The gas has this ideal gas and also the reality of it. So let's look at both sides. For the ideal gas, you're looking at gas that has no volume. When they collide, it's perfectly elastic, meaning that there's no interaction. There's no intermolecular force that makes them sticky. But when they come, they just kind of bounce off of each other. Also, they don't stick to the walls of the container. So there's no intermolecular forces between them that cause them to be sticky or hold on tight before even they bounce off. But of course, the real gas isn't much like this. It does have volume. And the collisions are not perfectly elastic. They will have the intermolecular forces between them, which can affect vapor pressure. Nevertheless, there's an important equation that you should know, and that is the ideal gas law equation. Why do we use this even though all these gases are not technically ideal? And this is because it really simplifies the calculation, although it's not exact, but it's very close to the real gas, resembles close to the ideal gas, and we can have a general estimation how a state of a gas might be. Through this particular equation, let's dive in a little further. We have pressure, ATM in units, and units is important. You can't have torr or any other units here. Volume would be in liters. The N represents moles. The T represents temperature, and that is Kelvin. And that you probably see a new variable, and that's R. And that R is a gas constant. It has a value, 0.08206 liter.atm, meaning liter times the ATM all over K times the mole. So this whole thing is 1 unit. The ideal gas law, we use this when we want to identify within the given moment, not between two states, meaning we don't have two pressures here, initial pressure, final pressure, initial volume, final volume. You see only that pressure, just one volume, 1 mole, 1 temperature. So you're looking at what is the pressure when you have this temperature, this moles, and this volume. What is the pressure? Not comparing when it increased the volume or when it decreased the volume. That's not when we're looking at that. We're looking at combined gas law when we're comparing. But right now we're looking at ideal gas law at that given moment, at that state. And also, these are gases that that are said to be behaving ideally, as I have mentioned, although not it doesn't behave ideally. There is real gas, but it is a great estimation of how the gas might behave. What is a volume of 1.00 mole of ideal gas at 0.00 Celsius and 1 ATM? Report the answer in 3 sig figs. So I'm going to write my volume as 1.00 moles. I'm going to write the temperature as 0.00 Celsius. And pressure is 1.00 ATM. And I'm looking for volume. Based on the ideal law equation, PV is equal to nRT. We are looking for V, so I'm going to divide both sides by P. That will cancel out the P, and V is equal to nRT over P. The number of mole is 1.00 moles. My R, okay, is 0.08206 liters ATM all over moles dot K. And then we have my temperature. The temperature right now is at 0 degrees Celsius. 0 degrees Celsius is 273.15 Kelvin. Same thing. So you needed to convert the Celsius into Kelvin. My pressure is 1.00 atm. So let's go ahead and calculate this out. 1.00 times 0.08206 times 273.15. So that's all of this right here, okay? And then hit enter. I have 22.4. Divide that by 1, which will be the same thing. 22.4. Now, I know it's liters because we're looking for volume, but let's go ahead and cancel out all the units. So if you look at this mole is on top and the other mole is on the bottom. Same for Kelvin. Here's Kelvin on top and bottom, and then ATM, top and bottom. So we're left with liters, so it works out.